Welcome to the IMSc Algebraic Combinatoric Seminar. And it's a great pleasure today to have Sami Assaf from the University of Southern California. And she'll be talking about Pieri rules for polynomials. Sami, please.
Thank you. It's really hard for me to watch the chat while I'm doing this, but I'll try. But you're welcome to interrupt me with any questions that you have as we go. Let me get my slides. Should come up. Okay. Let me see if I. Yeah. Okay, there's a chance that I'll see it. So if anyone has a question, you can put it in the chat. I might be able to see it, or just jump in. So I'm going to assume that people aren't familiar with key polynomials and that you may have never seen them before. So I'm going to try to motivate them. And everything I'm talking about today really comes from representation theory. So I'm going to be doing everything with combinatorics, but it all comes from the representation theory that's behind it. So here's the plan of my talk. It has 3 halves. So first I'm going to introduce the polynomials, and they all come up as characters. So this is the character theory section, but I'm going to be giving you combinatorial models for how to think about these things, because what I want to be able to do is tensor product things. So that means multiplying, and that's where the Pieri rules are going to come into play. And then the key polynomials are a generalization of Schur polynomials. In the Schur case, we get positivity, and we don't get positivity in general. And I want to sort of motivate why that is, but also say that, a lot of times we do get positivity, and there's interesting reasons why we get positivity. So we're going to get a rule that's going to have signs and look at cases where the signs are all positive. So polynomials. The basic objects in combinatorics are partitions. I don't think you can do combinatorics without them. So my partitions are going to be weakly decreasing sequences. I want to fix the length to be n, and it's fine with me if they're greater, if they're positive or non-negative. It doesn't matter yet. So Schur defined he characterized the irreducible representations of GLN. These are modules that we can write down, and we can take their characters. And this was the definition that Schur was working with. So the definition of a Schur polynomial is the character of the irreducible representation of GLN. Okay, and that's maybe not the most enlightening definition, so we'll have another one in a minute. But let's do an example. So the picture that I've drawn here is the picture of a crystal. And if you're not familiar with crystals, that's totally fine. But I think you've had Anne Schilling talk in the seminar, so you should have seen crystals a few times. I'm not going to be talking about them, unfortunately, in this talk, but I'll draw the pictures anyway because they're pretty. The examples that I want you to keep in mind as we're doing the irreducible representations are the 2 extremes. So if we have a single row, that's going to correspond to a single part of your partition is non-zero, and that's going to give you the symmetric powers. And at the other extreme, the conjugate of that is where your biggest part is size 1, and that's going to give you the exterior product. And then anything else, any other partition you have sort of interpolates between these 2 extremes. And so, for example, 2, 1, 0 is neither the symmetric product nor the exterior. It's something in between. Okay, but like I said, I'm going to be interested in taking characters. So instead of working directly with the modules, I'm going to be doing everything through character theory. And what are the characters for these 2 extreme cases? For the symmetric powers, we have the complete homogeneous symmetric functions. So that's the sum over all monomials of total degree m. Okay. And then at the other extreme, we have for the exterior product, the elementary symmetric functions. These are going to be multiplicity-free monomials of total degree m. Okay. So I'm not allowed repeats. And I'll move my mouse. And one thing we can do when we have modules around, it's fun to tensor them together and see what we get. And when we say what we get, what we mean is let's decompose the module that we get from the tensor product into irreducibles. And let's look at the multiplicities that arise. We can think about these multiplicities in terms of characters. So if we just take the character of that top expression, we get the bottom one, which is just a statement. This one is just a statement on the level of polynomials. It's saying that when I take the structure constants of Schur polynomials, I get these Littlewood-Richardson coefficients. That's what they're called. And they're the same numbers as up above. So if I can do everything through characters, I just multiply characters, and it's like tensoring representations. And now I'm going to explain what these pictures of the boxes are, which are probably familiar to everyone, but I'll describe them anyway. Combinatorially, what are the objects that index a basis for the representation? These are going to define our Schur polynomials combinatorially. So we're going to start with a diagram of a partition. And here I'm thinking of GL5. Okay, so I have 5 rows. One of them you can't see because it's empty. And I put lambda I boxes in row I. So here's an example, 54410 GL5 is what I'm thinking of. The row condition comes from when I have a single part that's non-zero. Okay, then remember I get every monomial. So that's telling me that I can repeat numbers. And I care about the set of things that I get. So you might as well put them in increasing order so that you don't write the same thing twice by accident. And the conjugate of that, I had multiplicity-free. So that's why I get a column strict condition. Okay, and then interpolating between them means just keep those rules. So we have weakly increasing rows, strictly increasing columns, fill it out, and that's the semistandard Young tableau. And we can write down all the tableau for a given shape. I need to tell you what GLN is. I need to know what that N is. So for this example in the middle, N is 3. So I'm not allowed to use a number bigger than 3. And then I just put them in these boxes in all possible ways. There are 8 ways to do it. This corresponds to the 8-dimensional module that we saw before. Taking the characters, I can do combinatorially. Oh, there we go. So looking up here at this example, if I want to take the character for, or if I want to take the weight of this object, I can think about in each box, I change the letter I to the variable x sub I, and now I multiply all my boxes together. And then that's going to give me the monomial corresponding to this object. Add those up for all the objects I can write down, and that's the character. So that's the theorem, is that these are the Schur polynomials. Combinatorially, so you could forget about all representation theory and pretend the talk started on this slide. And then one thing to point out is that the Schur polynomial in general is not multiplicity-free. The monomials can have multiplicity, and that corresponds to multiplicity in a weight space. And I'm going to talk about weight spaces in a minute when we generalize this. But for now, maybe the only thing you need to remember is Schur polynomials are fantastic. They are the best ever basis for symmetric polynomials, maybe. You could certainly make the case. And so we can do a lot with them by studying this combinatorial model. All right, so that's classical stuff. Everybody knows that. So now let's generalize it. And to begin my generalization, I'm going to start with the representation theory. So let's go back to GLN. And we have an irreducible representation. It's indexed by a dominant weight. So, but we can write it, we can decompose that representation into its weight spaces. So those are just the regular weights. And in the case of GLN, this is just weak compositions. Okay, so sequences, ordered sequences of numbers that are non-negative. Now, in V lambda, I have certain extremal weights. Okay, these are the weights that you get by rearranging the parts of lambda. Okay, that's an extremal weight. And the symmetric group acts on those, and it's a really nice action. It's a symmetric group because that's the Weil group for GLN. Okay, and they're all one-dimensional. We get a nice action of the symmetric group. So keep that in your head. And now what we're going to do is actually what Demazure did. So I'm starting with this module here, and what Demazure said is, let's look at an extremal vector. And what I'm going to do is instead, like this guy, instead of letting all of GLN act on it, I'm only going to let the Borel, the upper triangular matrices, act on it. Okay, so instead of letting any matrix act, only the upper triangular matrices act. So I'm only going to get a piece of the module. I'm not going to get the whole thing in general. But I can still take the character and, oh wait, I'm not taking the character yet. Well, let's do the module. So let's start at the top. So these Demazure modules, we have to take an element of the Weil group and a dominant weight. So here for this example, I'm going to fix this dominant weight to be 210, and I'm going to let my element of the symmetric group, my element of the Weil group, vary. I'm going to start at the identity. Okay, if I start at the identity, I'm taking this guy. I'm not changing the dominant weight at all. The dominant weight is 210. Okay, and now think of upper triangular matrices as taking you up. There's nowhere to go. It's the highest weight. You cannot go up. So you just get this one-dimensional space, and that is what this Demazure module is. It's this one-dimensional space. It's pretty boring. Okay, but now let's go up in Bruja order. For the permutation, now I'm at the permutation 1, 3, 2. So that's S2, the simple transposition that switches 2 and 3. Now what am I doing? Well, this is my extremal weight that I'm going to take. The extremal weight that's 201. And I'm going to go up. And again, what does up mean? It means you're acting with upper triangular matrices. Okay? And what do I get? Well, I'm going to get the highest weight vector as well, but that's it, just those two. So now I have a two-dimensional space. So let's lengthen our permutation again. Let's multiply by S1, the simple transposition that swaps 1 and 2. Okay, now what do I get? Well, now this is my extremal weight. If I just let that weight act on the dominant weight, let that permutation act on the dominant weight, this is my extremal weight, 0, 2, 1. And now I get everything up. Now, okay, it's not just reversing the arrows. There's something more subtle because I've drawn a crystal here, and a crystal is a deformation, and it's not giving you the full Chevrolet generators because we've deformed them. So there's a lot that I've left out. Okay, but there's some way that I can describe this set that I'm getting. So I have this 5-dimensional submodule. Okay, that's interesting. And now let's keep going. And now we're at the long element. We're at 3, 2, 1. Okay, and by the time you're at the long element, you're down here at the guy who's reversed of the dominant weight. So this is 0, 1, 2 is the weight. And everything sits above you. So you get the full module. So as we let the partition, we fix the partition and we let the permutation, the element of the vowel group vary, we're interpolating between the highest weight and the full module. Okay? That's what a Demazure module is. It's a filtration. You can think of it as filtering between the highest weight and the full module, and it respects Bruja order. So if you have two permutations related in the weak order, then the modules are contained in the literal sense of it. Okay, so there's something really nice going on here. And Demazure came up with this in the context of Schubert polynomials and Schubert calculus. So
excuse me.
Yeah.
Yeah. Are you saying that you can read it off fully from the crystal?
Oh, yes.
Okay.
Yes, you can read everything off from the crystal. The crystals are all powerful, and I can say more about that later. But yes, you can read it off from the crystal. So let's go back to that crystal, the nice one where things are kind of dead. So here I've sort of drawn these guys because they're the pieces of the module you don't get for this example where I've backed up my permutation a little bit. So sometimes when you act with the permutation, you don't do anything. Like if your partition has two parts that are equal and you switch them, you haven't done anything. So indexing with a dominant weight and a permutation is a little bit redundant. And in order to remove that redundancy, let's re-index things. Let's let the permutation act on the partition, and let's just index it by the composition that we get. And that's reversible because there's a shortest in Coxeter length permutation that sorts the permutation. The partition. I'm not going to get those words right tonight. So we really want to index these characters. So I'm now looking at these characters. We want to index the characters by compositions because it's a more efficient way to do it to avoid redundancy. Because sometimes these containments in Bruja order are equalities, depending on your dominant weight that you chose. So what are these two examples? So I've given these two examples of the module. You get the highest weight. What's its character? Well, it's just the highest weight vector. That's it. One monomial, and its exponent is the highest weight vector. And at the other extreme, if you take the full module, you get the full character. So we're interpolating between this leading term and the full Schur polynomial. So what we get in general is not symmetric, okay? In fact, if you run this over all weak compositions, what you get is a basis for all polynomials. So it's everything, okay? But we have a basis, which is fantastic, because when you have a basis, you have well-defined structure constants. I can multiply two of these characters, which I'm going to call key polynomials when we're in type A. These were studied under this name by Lascaux and Schutzenberger. This Demazure construction works for any Lie type, but key polynomials specifically are type A. That's what I mean by that. So we can take their structure constants, and when we do, we get negative signs. And the reason from the representation theory is because this idea of taking the Borel and letting the Borel act is not going to play nicely with tensor products for GLN, okay? Because the Borel doesn't quite see it right. So we're going to get pieces that kind of get crunched up together, and there's negativity, and we want to try to make sense of that, or at least I do. So a lot of times in combinatorics, we get really scared of negative signs. So I'm going to try to encourage you to be bold and embrace the negative signs that come up. And let's try to understand why they come up and where they come from. Because sometimes they're not there. And when they're not there, it's really exciting. And there's lots of interpretations. So we want to understand them even when they're there. So that's the motivation for key polynomials. This is where they come from. Let's see if there are any questions. All right, then how are we going to understand them? Well, I don't want to think about them in terms of, oh, just like don't take certain tableaux. that's kind of a hard way to understand it. This construction is fantastic, but it's not going to help me do combinatorics. So I need a combinatorial model. There are lots of models. My absolute favorite, hands down my favorite, is due to Axel Kohnert, who's a computer scientist who worked with Lescaut. And he came up with a gorgeous algorithm that I absolutely adore. I'm going to rave about this. So what we do is we start with a composition diagram. Okay, this is like a partition diagram. Please? Yeah.
I missed a part of your first part of your talk, a few minutes. So once again, could you key polynomials are just characters of Demazure? Is that correct?
Yes. This is the first time I defined key polynomials was this slide. You did not miss much. Key polynomials are characters of Demazure modules in type A.
In type A. Okay. And
in type A. Everything I'm doing in this talk is type A.
Okay, and you're just multiplying them and trying to find the structured constants, which could be the
yes.
I understand.
Yeah.
Thank you.
Absolutely. Okay, so to multiply them, I need to do combinatorics because at the heart of it, I'm a combinatorialist. I only dabble in other things. So here's my dabbling here. So Kohnert says that you're going to draw this composition. So the 4 here tells me there are 4 boxes in the first row. The 1 tells me there's 1 box in the second row. The 5 boxes, 0 boxes, 4 boxes. And now just so you don't get confused and think that we're really doing things with boxes and tableaux, I'm going to draw them as bubbles. Okay, and Kohnert really thought of these as champagne bubbles, and he had his thing upside down, so the bubbles kind of floated up. So keep that in mind. Our bubbles are going to float up, except that I've reversed gravity, and I apologize to Kohnert for that. But we take this composition diagram, and now we're going to do moves on it. Instead of putting numbers in the boxes, I'm going to move the bubbles. Okay, so here's what you do. You pick a row, any row. I'm picking this row, and I'm picking this bubble. Okay. And I push the bubble down. Okay, that's it. This is a Kohnert move, and now I have a new Kohnert diagram. And I can keep doing this. Okay, so let me take that bubble and push it down again. You might complain that this bubble's in its way, but what Kohnert says is that that's really fine. Just jump over it. Okay, all right, fine. So I jump my bubble down here. Now what can I do? Well, just pick some more bubbles. Here's a bubble. End of the row, so it's a fine bubble to pick. Push it down. Okay, great. Take another bubble. How about that one? Push it down. Doesn't matter what order, I just go nuts with it. We're looking at the set of things we can get. But be careful. You can't take this bubble, right? If you take that bubble and you try to push it down, that's not a Kohnert move, right? Kohnert says take the end of a row. But if I push it down anyway, the interesting thing is that what I get, while the moves that got me there are illegal, the end result is fine. Because I could think about if I push these 3 bubbles down from right to left, okay? Those are Kohnert moves. And then push this bubble down, and then push that bubble down. I end up exactly with this sequence of bubbles getting pushed down here. So I can get there with the Kohnert move, just not the one that I did. So it's still a Kohnert diagram. And that's one of the troubles with this algorithm is it's kind of hard to tell when you've got everything, and it's kind of hard to tell if I just give you something if you can get it. Okay? But I still really like this, and I'm going to try to convince you in this talk that this is a fantastic model. So let's do a big computation. Let's compute all the Kohnert diagrams for this composition 0 to 1, all the Kohnert diagrams. So we start with 0 to 1. Okay? Now what can we do? We've got 2 choices of boxes to push down. So let's push those down. These are the other 2 diagrams I can get. Now, on this guy on the left, I could push this one down or this one down. And over here, that's the only thing I can push down. So let's just do the pushes. Well, I said there were 3 things I could do. How come I only got 1? Well, if I push this box down, or this bubble down, or I push this bubble down, it's the same thing. And I'm counting a set. So I don't care how many ways I can get there, only that I can get there. So these are the objects that I can get. There are 5 of them. Remember that 5-dimensional module that we had before? That 5 is the same 5. And I'm going to point out this is no good. It's not, this condition isn't just kind of willy-nilly. You can't get this thing. And you can easily convince yourself that that red ball, there's no way for that ball to get there with the other bubbles staying where they are. There's no Kohnert move. There's no sequence of Kohnert moves that'll let you do that. Okay, so that guy's out. So what's the weight? Well, I'm not putting numbers in the bubbles. I'm moving the bubbles. So what matters is not what's in the bubble, but where the bubble is. So that's how I get my weight function.
I have another question, please, if
yes.
you don't mind.
Yeah.
So I didn't really understand what the Kohnert move is. Why can't you push so if you push the bubble on top, it comes down all the way.
Yes. It comes to the nearest, if I push this bubble, it comes here. It comes to the nearest available spot.
So I cannot push a bubble down when it has something below it, or what is
You can push a bubble down. So this one says you can push a bubble down. As long as, here's the important thing that I think you're missing, it has to be the end of its row.
Okay.
You only push from the end of a row. So I can't push this bubble down because it's not the end of its row.
Yeah.
So that's why I can't get this.
Can I also ask one question? So can you explain me the third one? How did you get that? The third one in
this one?
Yeah. Yes, exactly. How did you get this?
This one came from pushing this bubble down. It jumps.
But then it was not the left. I mean, the one that you jumped is not the.
It doesn't matter who you jump. It only matters who you push.
Oh, okay.
You get to jump. So you can jump across anybody you want. It's just you can't push a bubble that's not the end of its row. But you can jump a bubble that's not the end of its row.
Okay.
It's not an obvious, I mean, it's a bizarre algorithm, and you might wonder what this has to do with anything, which is totally fair, but it's brilliant. Please believe me. I will convince you of this.
But they just come from the crystal operations.
I will explain. So Kohnert moves are not crystal moves. And crystal moves are not always Kohnert moves, but there's a very nice connection between crystal moves and Kohnert moves. And I'll say more about that.
The effect of the weight is also not the same because you're jumping.
Not at all, because the jumping really screws you over. Yes, that's exactly right. And that's the beauty of Kohnert moves. I will try to remind me, and I'll say more about that at the end.
Okay.
So here's the weight. Look, the weight is based on what row you're in. So here there are three bubbles in row 3.
Let me ask you a question. So if the bubble just falls one step down, if such is your
what is what?
In that case?
If the bubble moves one step down, what is what?
No, I'm just modifying Amri's question. Is that a root operator on the crystal? That was the question, right?
Not necessarily.
Even not even if it moves.
So I'm not going to talk about the crystal yet because I haven't even defined the crystal, and I'm not really going to talk about the crystal in this talk, but I can say more about it at the end. Okay? Because I haven't defined crystal operators, and that's a whole different talk I could have given. You guys should have told me you wanted that talk.
No. We'll ask you later. Yeah.
Yes, do ask me though. It's fascinating, and I think it's fascinating, and I love it. So please ask me later. But the point is that the weight here comes from the rows. So you can think of every bubble in row I, put an x sub I in there, and now multiply your bubbles together. The bubbles are moving, so that's changing our weights. Okay? So we take the polynomial, and the theorem of Axel Kohnert in his thesis is this is the Demazure character. This is the key polynomial. This defines the key polynomial. Somehow it gives you exactly the right set of objects. It's amazing that it does this. Okay, so I want you to have some intuition for this. And this is kind of a bizarre rule, as I think we can agree. So I want to try to explain to you why it's the same as tableaux sometimes. Oh, sorry. First, I have to tell you that key polynomials are not, in general, symmetric. This example is not symmetric, for example. They're a basis for the full polynomial ring, right? Not just symmetric polynomials. But remember that sometimes a key polynomial is a Schur polynomial. And in fact, every Schur polynomial is a key polynomial. It's just not the converse. So we should be able to come up with some dictionary between tableaux and Kohnert diagrams. And here's the map. So I have a 7-year-old, and she can do this map. So you can do this map too. Here it is. Start with the bubble diagram. This is the one that I picked before. Okay. This is the first step's the hard step. You ready? From the bottom, put n's in row 1 and then n minus 1 in row 2. So there's n minus I plus 1. That's the part that can trip you up if you're 7. I'm sure you guys can handle it. Now you fill the bubbles with helium. Let them float up. Don't let them get out of order. Don't let them change their columns. Just let them float up. Okay, and now make them square. That's the whole map. It's really not complicated. What does this map do? It's weight reversing. Notice that down here, I'm going to get x1 to the 4th. But because of this, I'm only going to get the x1s are up here. Wait a minute. So x1 to the 4th corresponds to 4 5s. So it's reversing the weight. Okay. That's fine, but it's an injective map. And here's the example. So these are the 5 guys we did before. Here's how you inject them to Tableau using this, fill them in helium and make them square. And it's a bijection if and only if you're in this case that we set up at the top. Okay, so you miss terms unless you have everything. Sort of a stupid way to say it. And just because you guys keep bugging me about it, I'll say that if you want this to be a crystal map, which why wouldn't you want it to be that? You need to compose it with the Schützenberger involution that basically flips the crystal on its head. So that undoes the weight reversing. And if you do that involution, the crystal involution, then this is a crystal map. This is your dictionary between crystal moves and Kohnert, well, on Kohnert diagrams. It doesn't quite tell you what the Kohnert moves do, so let's not go into that yet. But it does tell you that this respects the crystal. And again, I'm not telling you what a crystal is, so if you don't know, sorry, but we'll talk about it at the end.
I have a question.
Yeah.
I wanted to ask, you said that multiple sequences of Kohnert moves can result in the same diagram. So I wanted to ask, is there a significance to the multiplicity of a Kohnert diagram that can be obtained?
That's a great question. Not that I know of. Somehow what matters about the Kohnert diagrams is the set that you get, and how you get them is a mess. It's honestly just a crazy mess. It's somehow exactly the right thing to do, but God only knows why. It's a mess. There's no nice structure. The Kohnert poset, if you think of these moves as making a poset, it's not ranked, it's not a lattice, it's not got any nice properties at all. It doesn't have a unique minimum element. Like it's awful. And it's exactly the right thing to do. Go figure.
Okay.
Here's something more bizarre though. Okay, this diagram over here, I mean, this is the one that we got. I'm going to keep this as my example throughout the whole talk. I just picked one example. I'm totally lazy. So this is my one example, guys. So this one example we saw was a Kohnert diagram for 4, 1, 5, 0, 4. It's also a Kohnert diagram for 0, 1, 4, 4, 5. Because I could take this guy and pretend they're bubbles again, move all the 5s down to row 1, then move all the 4s down to row 2, and do it from right to left, of course. And then the 3s down, and then the 2 down, and that will give me, that's a recipe for getting this thing. So if I just give you a diagram and say, hey, this is a Kohnert diagram, do you know what it's a Kohnert diagram for? You can't answer it. It's a Kohnert diagram for lots of things. It's not well defined. If I give you this tableau, you know what the shape is, but somehow you don't know what the ambient shape of a Kohnert diagram is. That information is lost by the algorithm. Because you could start with your bubbles super high up and just push them down, 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 and you forgot that they were really high. You have no way to remember. You only know where they are, not where they were. So you lose information, and that's important. It's part of why this rule is tricky to work with, but it's also the incredible beauty of this rule. So that was all I was going to say. So hopefully now you fully understand Kohnert's rule and key polynomials, and you're ready to multiply. But first, we'll start with multiplying boxes, and then we'll multiply bubbles. So Schur functions are a basis for symmetric functions. Their structure constants are well defined, and because they're counting multiplicities when we take tensor products, they're non-negative. So how can we think about those? Well, Pieri, even before Schur was doing his work, Pieri told us how to multiply Schur polynomials. So if we want to multiply a box, classic Pieri case, we want to multiply by a box. What do? We take our partition. I only have one example of a partition. Well, maybe I have 2 examples, but this is one of them. So we take our example, and all we do is add a box in all possible ways so that we still get a partition. So I could add it down here. I could add it right there. I could add it right there. I could add it right there. That's it. No other place of putting that dot is going to give me a partition. So that is my expansion. It's a beautiful statement. I mean, it's fantastic. And you can multiply by a row, right? So if I want to multiply by 2 boxes, Let's take this shape and multiply by 2 boxes. What do? I just add 2 boxes. Except, I have a caveat. Because I'm doing this horizontal strip, I'm doing this, I'm multiplying by the symmetric power, not the exterior. There's another rule for the exterior. I'm not going to talk about that. But let's do the symmetric power. I want to make sure that I don't add 2 boxes in the same column. Okay, so if I'm going to add a box in column 1, I can only add 1 box in column 1. But I could add another box in column 2. That's fine. I could add them like this. I could add them like this, or like this. And that's it. That's the only way to add 2 boxes where you're not adding 2 boxes in the same column. Okay, so that's my expansion. It's an absolutely fantastic rule, and it's multiplicity free, which is interesting. So this is the branching rule for Schur polynomials. And we're using this poset structure of Young's lattice, which is really Bruja order in disguise. So you just go up by adding a box. I want to say a word about how you prove it, partly because it's a gorgeous proof and partly because it's important. So I'm going to use the RSK algorithm to prove it. How does RSK go? I'm just going to remind you this. It's an operation on tableau. You take a tableau and you take a number. A number is a tableau with 1 box. Okay? And I'm going to push the number into the tableau in such a way that I get a new tableau. Okay? And the way it works is I take the number 2 and I'm going to scan by rows. Okay? And I'm going to look for the leftmost thing that's bigger. And I'm going to say, okay, it's that 3. It's the leftmost thing that's bigger than me. I'm going to knock it out. Fine, now the 3 is in the next row down, and it's looking to land. So it's going to look for something bigger, the leftmost bigger thing, knocks it out. Now the 4 is looking, leftmost bigger thing, it's the 5, knocks it out. The 5's looking, nobody's bigger than the 5, so we're in this case, so we just land. Okay? That's RSK. It's absolutely gorgeous. You need to prove lots of things about it. It takes forever to prove anything about it, but it's somehow all very intuitive. And it gives you a bijective proof of the single box case, because what we're proving is that we have we take a tableau and we take a number and we get another tableau, and this is a bijection. And of course the shapes are different for what I get, so I have a disjoint union. And there's a row bumping lemma that says if you take weakly increasing numbers, that's the single row case, that you don't add in the same column. That gives us the column statement. And because my term in my Pieri rule, each of those diagrams is a different shape, I have a disjoint union, so I can just take the generating function, and this proves the Pieri rule. And we're totally inverting history here. But this is one way you can prove the Pieri rule. It's a fantastic, beautiful proof. So I want to try to do this for key polynomials, knowing that I've got a lot of work to do because, well, here's what I want to do for key polynomials. So Schur polynomials at the highest level, what happens? I take my partition and I add 1 to some part. And I do it in a nice way so I get a partition, but that's what I do. Okay, so E sub j is now it's not an elementary symmetric function, it's the jth canonical basis. So the jth entry is 1 and all the other entries are 0. I'm adding a vector. So I want to try to do that with key polynomials. Can I just do it? Well, with key polynomials, with Schur polynomials, we just have S1. There's only one way to add a box, but with key polynomials, I have to choose where that box, the bubble that I'm adding is. What row is it in? Here I've decided it's in row K. Okay, but all right, can I write this some way? Well, let's do an example. All right, so we're doing my favorite example, which is 41504, and I'm going to multiply by a box in row 3. Okay, or by a bubble. Sorry. Well, I can see that trouble awaits. It's not positive. I'm screwed. But let's just try it anyway. And again, I want to keep this paradigm in mind. Can I think of the answer as adding a bubble? So let's take this term. Did I just add a bubble? Actually, I totally did. I added a bubble in column 2. Okay, that's awesome. And that's below row K. That's below row 3. Because remember, I have in my head Kohnert's rule, which is things move down. So if I'm adding a bubble in row K, I kind of want it can go down, but I somehow don't want it to go up. That would somehow really disturb me. Okay, so that's fine. That term's great. What about the next term? Actually, this is perfect too. I've added a bubble in row 1. That's fantastic. So this, again, we can compute this on the computer, and that's where we did all of our initial testing, is we just threw it on the computer. It's a basis. You can just triangulate. Okay, cool. So what about the next term? Well, okay, we're screwed. Yeah, there's no way, you can't write this as the composition we started with, adding 1 to a part. It's not. But is there some way we can make sense of it, knowing what we know about Kohnert's rule? Well, yeah, what happened? This 4 kind of moved down. And that's a Kohnert thing to do. What happened is these 3 bubbles dropped down by Kohnert moves to these 3 pluses, and then we added a box. So that's the paradigm. That's the way I'm going to interpret that term. It's a Kohnert move, and then I added a box, and that's fine. Somehow that doesn't bug me. I can do Kohnert moves. Let's pretend the negative term's not there for a minute, because that really does disturb me. Let's just do the last term, and oh, that one works too. So except for the fact that we have a term with a negative sign, everything's just peachy, right? We can interpret those terms. Okay, but we have to reconcile this negative term. And here's the beautiful thing. Kohnert diagrams are not, they don't tell us their shape. They don't tell us where they came from. The Kohnert diagram of shape, the composition diagram of this shape is actually lives in this set and in this set. And in fact, if you take these 2 sets and you take their intersection, it's exactly these Kohnert diagrams. So the fact that the Kohnert diagrams are redundant is exactly what's happening with this. So the negative terms that we get in the expansion are if we think about things as unions, and we remember that we have to do inclusion, exclusion. So the intersections of sets of Kohnert diagrams are exactly the negative terms. And then we can get lower terms. It doesn't have to be just 2. So there's something positive going on. And that's our first theorem, is that we actually can think about this as a bijection. There is a bijection from Kohnert diagrams of a given shape, add a bubble in row K, and we get this less than or equal to is what we call the left swap order. This came up in earlier work of myself and Dominic Searles, and all it means is move bubbles down. So if you can get one composition from another by moving the bubbles down, then it precedes it in this order. This is incredibly redundant, the way I've written it here. It's incredibly redundant. We have a tight expression for what the terms are that you need to write down. But on the level of the bijection, this is the most elegant way to say it. And now when we take generating functions, all we do is apply inclusion, exclusion, and that pops out the formula. So I was really happy when we found this, because it somehow, like, inclusion, exclusion doesn't bother me, right? I understand about derangements. And this makes the negative signs make a lot of sense to me, because these modules, there's a filtration of the modules, but these pieces of the modules that we're taking are not disjoint. So there's actually something happening at the level of the representations as well. So it's not just a combinatorial contrivance. And so we have a theorem that's a bigger theorem, which is how do we do rows? So ignore the notation there, and just, here's the rule. You drop, add a box, drop, add a box, drop, add a box. Don't ever add in the same column. So here's an example. So my example for partitions when I was doing the 2 boxes was 2, 2, 3. So I'll do 2, 0, 3, 2, and I'm going to add in row 3. Okay. The rule is pick your columns you want to add in, drop boxes if you have to, drop the bubbles down if you have to. Otherwise, just take the term. Here I could just add bubbles in columns 1 and 2. If I want to add bubbles in columns 1 and 3, there are 2 ways I could do it. Okay, I could just add them right here and here, or I could add this bubble and then drop this box down, this bubble down, and then add. And whenever I can do something in more than one way, I'm going to get a negative term. I'm going to get some intersection. So not only do I know where the negative terms come from, but I know exactly when they show up. And so I know exactly when the expression is going to be positive. So if I keep going, I get a positive term. I'm going to get 2 ways to add in columns 3 and 4. So I get a negative term and 1 way to add in those columns. So this is our main theorem. And again, if I wanted to throw even more notation at you, which I don't, because it's late for me and it's early for you, and neither of those is a good time for notation, we can write down exactly what this expansion is just in terms of the compositions. We can write a tight formula for it where every term counts exactly once. But it does involve an obscene amount of notation. So I want to tell you a little bit about our proof. Are the multiple? Yes. Oh, great. Thank you for that question. Yes, it's multiplicity free. The multiplicity is always either 0 or plus or minus 1. That's a great question. Absolutely. And it's shocking. Like, why would you expect that? I wouldn't, but it is. Absolutely. Totally multiplicity free. There's no overlaps. So it's the same phenomenon that was happening in the Pieri case. Great question. Thank you. Okay, so I want to tell you a little about our proof. And to tell you about our proof, I have to tell you that actually Dominic Searles, who's at the University of Otago, where they have like no COVID on the whole island, he and I came up with a characterization of which diagrams come from some composition diagram by Kohnert. Because if you just write down some bubbles in space, they might not have come from any composition diagram, right? And we found a way to tell if they did. And there's a formal definition, but let me draw you a picture. Okay, so you look in column 2, and you say, from the top down, you say, is there a cell in column 1 that I could connect with that's weakly above me that I haven't already picked? And you just connect them up. And then you go from column 3 to column 2. Can I connect to something in column 2 that's weakly above me that I haven't already picked? And then you go on and you go on. And if you connect everybody who's beyond column 1, then you're a Kohnert diagram for something. And if you can't do it, then you're not. Okay? So it's an if and only. If you come from Kohnert moves on a composition diagram, if and only if you can do this matching between columns.
So wait, this one bubble over here, is that bad or is that good?
This one? This is fine because it's in column 1.
Okay, so column 1 is okay.
Column 1's always fine. Column 1's always fine. So this bubble's fine. I should have probably drawn those bubbles there, but I honestly couldn't get Tix to do that for me. So, okay, so I want to tell you about this process called rectification. And I'll go ahead and give you a spoiler. It's RSK. Okay, what I'm going to do is RSK bubble style. Okay, so I'm going to insert a bubble into a Kohnert diagram. And here's what I'm going to do. If what I have is a Kohnert diagram, that's that lemma above, test it, then stop. So I try to do my test, and crap, it's not a Kohnert diagram. Okay, theorem, if it's not, then there's a unique bubble that doesn't get matched. Okay, if you do the greedy algorithm, it's deterministic. There's a unique bubble that doesn't get matched. Okay, so what you're going to do is push that bubble to the left, stay in the same row, push it to the left, 1 column. Try again. Okay, that red bubble still does not work. Push it to the left. Try again. The red bubble is now matched. Fantastic. Of course, this bubble is now a problem. But only 1 bubble is a problem. So push that bubble to the left. We just did a bump. We just did an RSK bump. Match it. And another spoiler, this is literally the same RSK example that I did before. It's literally the same under that bijection. So we bump again. This guy goes down, it needs to go over. Try to match it. Aha! Everybody matches up. We stop. The theorem is, one of our theorems is, this is RSK. Okay. Another theorem, because people have asked me about crystals, is rectification commutes with the crystal structure. That's why it works. In fact, it is the transpose of crystal moves. And that's why it works. And this gives us a bijection in the case when we have the sort of bar, the bubble we're inserting initially is high enough up. This proves everything we need to prove in the most beautiful way. It doesn't work in general. So what we have to do for the general case is a lot more subtle. We have to take we actually work with the image. We take the thing in the image and we decide on a piece of it that we rectify. And that pops out the data that we started with. That's how we reverse our map, basically. So there's a subtlety here. It takes us about 10 pages to define everything and state all of our theorems. And it takes us another 50 pages to prove everything. Just because the nature of these insertion type algorithms are just kind of hairy. There's a lot to prove. There's a lot of notation to build up. But none of the concepts is particularly complicated beyond this. So we've generalized RSK in a way that works. And I'm pretty happy with this one.
So do you monoid structure on these Kohnert diagrams?
Can I what?
Can you get a monoid structure on the Kohnert diagrams?
A monoid structure?
Yeah, like
I'm not.
monoid or something.
I mean, I'm not sure what you mean by that.
you know, for Tableau, there's the Plactic monoid.
Ah, oh, yes. Sorry, then I do know what you mean by that, and the answer is yes. That's already done. And there's a coplactic structure, and there's a crystal structure. Everything you want is there.
Okay,
Yes.
great.
Okay, so the final half of my talk, which is the shortest half, which is good. I'm going to tell you when it's positive. Because remember, we know when it's positive. It's positive whenever you don't have a choice in how you add in the columns. And in those cases, we get nice answers. So in the first example, and you can look at the theorem, this is really nice. When the point here is that K is at least the length of lambda of A. So when the number of variables that you're adding with is big enough, then there's no dropping that happens. You just go nuts adding bubbles, and you just add them. There's a unique way to add them, and that's it. You just add the bubbles. And the rule is that you always add the bubbles as high as you can. So if I want to add, if I've already added this bubble here in column 1, and I want to add a bubble in column 2, I take the highest spot, not this one. I take the highest spot I could. And that's the same thing that happened with Tableau. I mean, if you think about partitions, that's exactly what we did with partitions. If you have 2 parts that are equal, you don't take the bottom one, you take the top one. So this is as nice as possible. And the proof here is just rectification works. So it's the same old RSK proves this one. The bottom insertion, so now so that's when we have lots of variables. When we have one variable, x1, right? It seems weird if you want to multiply by x1 to the n, but it's something you could do. And the interesting part is expanding that back in terms of key polynomials, right? That's non-trivial. So what do? There you don't use rectification. You do something more naive, which is you put the bubbles in as close as you can. So as soon as you can, and you do some dropping, but it's also going to be multiplicity-free because you do dropping only if you have to. There's no 2 ways to do anything. And I'll say that this bottom insertion that we have that proves the rule at the bottom is not the same as rectification. It is actually different. And the general proof is fundamentally interpolating between these 2 cases, between the thing at the bottom and the thing at the top. And that's all we're doing. And when we have a general case, all we do is we break it apart to a top piece and a bottom piece, and we rectify the top piece and we leave the bottom piece alone. So we get positivity in these cases. And the last thing I want to say is that I care about positivity. So I think it's cool that I can understand the negative signs, but I care about positivity because really I'm not doing representation theory. And I'm not even doing combinatorics. I'm actually trying to do geometry. And the geometry that I'm trying to do is I'm trying to intersect Schubert varieties. And the way that we can do that using combinatorics is instead of working with the cohomology, which is this quotient by the e's of the elementaries, we can work with Schubert polynomials because their structure constants on the nose give us the Schubert structure constants. And if that's not familiar to you, that's fine. Just know Schubert polynomials are fantastic. And we don't know how to multiply them. They're indexed by permutations, and we do not know how to multiply them. We know very few special cases. Shockingly few, considering this has been worked on for 150 years. So some permutations are special. A Grassmannian permutation has 1 descent. This is the 1-step flag variety. The Schubert polynomial indexed by a Grassmannian permutation is a Schur polynomial. So Schubert polynomials are a different way to generalize the Schur polynomials to the full polynomial ring, because Schuberts are a basis for the full polynomial ring as well. Another thing you could do is there's this pattern avoidance condition that Lescu and Schutzenberger defined that is called Vexillary. Okay, and there's a 4-term pattern, there it is. If you avoid that pattern, you're Vexillary. If you're Vexillary and you're a Schubert, then you're actually a key. So Schubert polynomials sometimes coincide with key polynomials and not just in the Schur case. Okay, but there are keys that are not Schuberts and there are Schuberts that are not keys. They're different in general, but they do overlap. Okay, and the Larimer code gives you the indexing. So that's what the L is, the Larimer code for the Schubert. MacDonald flipped this notion of Vexillary, and I'm kind of running low on time, but so there's some condition on Vexillary, which basically tells us you want to compare when there's a long row, a short row above a long row. You want to make sure there's not too many short rows in between. That's fine, but the second condition is really exciting. So it says if there's a short row below a long row, you cannot have any shorter row in between. You can't have anything strictly shorter in between. So this is not Vexillary. But if I kind of move everything up to get rid of that row of length 0, then this is vexillary. And it turns out that this second condition, this one right here, is exactly what we need to ensure that our Pieri rule is positive. Whenever we have a composition that satisfies McDonald's second condition, we get positivity no matter what we multiply by. And McDonald proved that a permutation is vexillary if and only if its Larimer code is vexillary by this definition. And this happens if and only if the Schubert is equal to the key. So I want to multiply Schubert polynomials. I find that very difficult. So instead, I've decided to look at the vexillary Schubert polynomials. We can multiply the Grassmannian ones. Like, we know how to do that. Even if they're different Grassmannians, we know how to do that. There are rules for that. That's fantastic. That's like the only thing we know how to do, but we know how to do it. I'm trying to get to the vexillary case. And the shocking thing to me is that when we figured out how to multiply key polynomials, the vexillary condition told us that it won't be negative. Of course, the geometry tells us that too, but this was what was surprising. So this is my favorite corollary of our result, which is if I take a vexillary Schubert and a Grassmannian Schubert, I multiply them and I know what the expansion is in terms of key polynomials. And it's positive. And this is some of the notation you have to deal with to state things correctly. But let me just do a quick example. This was the vexillary composition that we came up with before. I'm adding 2 boxes. I can do drops, but I'm never going to have 2 ways to do something. And it's that second condition that tells me I will never get 2 ways to do something. It's always going to be positive. In this particular example, every single one of these key polynomials that I get is vexillary. So each one is a Schubert. So I've actually just multiplied Schubert polynomials for this example. In general, vexillary times vexillary is not a sum of vexillaries. So it's not going to get me everything I want. But it does seem like what we can do is we know that what we have been able to convince ourselves of is that vexillary Schubert times vexillary Schubert, we know how to write that in keys now. So that's not in our paper, that's newer, but we can write it in key polynomials, not in Schubert's, not yet, but it's at least a big step in that direction. And that is the end. I will leave you with these references, and thank you very much for your patience.
Was amazing. Thank you very much. Let's give her a big hand. You can unmute your mics and clap. The applause button doesn't quite do it for most of us. So.
I think it's fine. I see the claps.
Yeah. So, are there any questions? There's something in the chat. Oh, it says great talk. Okay. And,
Thanks.
I have a question, Amri.
Yeah.
I just want to understand this last bit. So vexillary times the Grassmannian Schubert is okay in the sense that you get vexillary and therefore they are you can write it in terms of key polynomials, but they're all vexillary Schubert. Is that correct? Therefore Schubert. Could you say that again, please?
That's not true in general. So in this particular example, it is. In this one example. And in lots of examples, it is. But in general, if you take vexillary Schubert times a Grassmannian Schubert, it's not necessarily vexillary.
Then what is your, but then what is the theorem that we are seeing? Could you explain that in the last slide? What is that?
This is saying that I can multiply Schuberts and write it as a sum of keys. So I will say the following. So this is also true that every Schubert polynomial is a sum of key polynomials, a positive sum, maybe with some coefficients. So we'll call them CAWKA. So this is true where these guys are non-negative. So, and I know what this expansion is. Everybody knows what this expansion is, not just me. So we're writing things as a sum of keys, but we still have to triangulate to get back to Schubert's. But Key polynomials are a much more compact way of keeping all that information than just monomials. So we're actually really close to the Schubert expansion. And these coefficients are small. Schuberts are sums of very few keys. So the hope is that we can somehow group our key polynomials together to get a Schubert expansion. That's a humongous step. It's really big and hard. So I don't mean to say that we know how to do that. But what we do know how to do is we know how to write these guys as a sum of keys with some coefficients that are non-negative.
Mm-hmm. Yeah, okay, that sounds like a very, very nice result. I mean,
thank you. It's a step that might lead to something great and might not be any easier than the hard problem that we're trying to solve.
Yeah, so can I ask you a question?
Of course.
So my question is, so like you said that when W is your Grassmannian, then the Schubert gives you the Schur. So is that analogy for the key polynomial?
That's the Vexillary condition for key polynomials.
Ah, okay.
So a Vexillary Schubert is a key.
Oh, okay, yeah, I missed that, yeah.
Yeah, Vexillary is where Schubert and key coincide. In general, a Schubert is always a positive sum of keys, and it's exactly one key polynomial when the permutation is Vexillary.
So earlier you said that from the representation theory background that the Demazure module's character is key, right?
Yes.
Okay.
So the key polynomials are the characters of the Demazure modules. And what Demazure was doing Schubert calculus, right? So he was looking at Schubert cells, and he wrote them as unions of these modules where the Borel acts. That's exactly this expansion. That's why I said everyone knows, because I guess Demazure knew, so maybe everybody knew. But this expansion comes from Demazure somehow. Okay. But like very geometrically, he took the Schubert cell and he broke it apart into these Demazure modules.
Okay, great, thanks.
So I have a question.
Yes.
So in the special case, when your key polynomial is the sort of just the highest weight vector alone.
Yes.
Is that, I mean, is that any easier in the sense of, so if you multiply a key polynomial with just this highest weight, not sure what I want to ask exactly, but so in terms of this Demazure modules, so this is like these, whatever it's called, excellent filtrations or whatever it is in the representation theory sense, right? So it amounts to taking a Demazure character and multiplying it just with the highest weight alone. So in that case, so your result encompasses that case as well, right? The Pieri rule.
Well, technically the Pieri rule, well, I mean, we could have that as the guy on the left. So the Pieri rule means that one of the things I have to take has to be a homogeneous symmetric function.
Okay.
In any number of variables. So we can do it when that guy's at the bottom. So when the variables are all x1. Okay. But in general, so we don't have a full understanding of key times key yet. So we have a rule that we can write down that we believe is correct, and we have not generalized our proof. Because our proof is fundamentally too messy to try to do for the general case. Like we think it works, but we think we also need to clean up our proof before we write down the new proof.
I see. So even in the case when you do key times just this single monomial, even there you're saying it's somewhat...
our thing is only a horizontal strip, right? And if you multiply by a monomial, you kind of get like, you can get funky shapes. Right. We only do a strip in this paper.
I see.
So it technically doesn't cover that, but that case is probably one of the easier ones to cover because the monomial, like it has to be stacked near the bottom. So all of your variables are kind of small and that's somehow that is easier to manipulate, but it's not covered in what we've done.
I see. Okay.
At least not in this proof.
Okay, thanks.
So yeah, I have a question. this when you, is there a representation theoretic interpretation for these positive and negative terms in terms of, you know, when you say tensors of Demazure modules?
So that's something I'm struggling with. Yeah, so I think I understand them geometrically more than I do from the representation theory. So if you think of them as living inside of Schubert cells, then you can see the intersection happening, and you can see where the inclusion exclusion comes from, and it kind of makes sense. But I don't know how to interpret the general Demazure in that paradigm without going through the Schubert cells, and you shouldn't have to. Somehow it's like you can define the representation. I never defined what a Schubert variety is. And somehow I shouldn't have to tell you about that to answer the question. So I don't know how to do it. So I'm not sure. I find that really interesting. I'm not sure.
I'm also a bit confused. So you said there's a monoid structure. But then, you know, how does a monoid structure lead to a negative term?
So when you ask me about the monoid structure, my understanding of it is limited in, I know what the plactic relations are and the coplactic relations, and these are basically in my mind like Knuth moves and dual Knuth moves. Okay, and we know what those are because we know what the right objects are to kind of pick out, and this is actually implicit in this paper with Dominic Searles. So there we talk about, we look at things in terms of what Dominic and I call the fundamental slide polynomials. And that's going to give you the analog of standard Young tableau. And then we do the analog of Knuth moves and dual Knuth moves on tableau. And but we do it on diagrams instead. So all of that structure is contained in that paper. So what you're looking for from a monoid, I'm not entirely sure because I guess I'm not familiar enough with it. But if what you want are sort of these Knuth and dual Knuth moves, we have them. And they're in that paper. And by the way, if you did want the crystal thing, there's a whole paper on crystals and Kohnert polynomials that I have.
Okay.
So we know how.
I mean, Schutzenberger just defined that. Schutzenberger just said that you take the free. Schutzenberger said that you take the free monoid and then you just take the Knuth relations as rewriting rules, and the monoid that you get is the plactic monoid. So he has this, you know, very simple, and then you just do multiplication in this monoid and keep track of shapes, and the Littlewood-Richardson rule falls out.
Okay, so the problem is you just said keeping track of shapes. So we know what those moves are. We know what the Knuth moves are. The problem is we can't keep track of shapes.
Yeah, it seems.
And that's where your negative signs come in.
Yeah, shape is not well defined. Right. Okay.
That's exactly where the negative signs come from. We cannot. It's not. You can't keep track of shapes. It has to be ambiguous.
Right. Got it.
But we do know what those moves are. We do know what those moves are. And somehow it predates this work.
Right. Let's see. Are there any more questions?
Seems like no.
Okay, so it seems that for now, people's curiosity has been satisfied.
It was an excellent talk. So once again,
let's thank Sami.
Yeah.
Also, if you'd like to share your slides, I can put them up on our website.
Oh yeah, I will. Will you let me